Digital System Series Part 2, Boolean Algebra Basics and How It's Used in Digital Systems. In the previous series, Part 1, the topic of the presentation was to give you the basis of Boolean algebra and the main gates used in digital systems. In this presentation, the gate XOR is being introduced. This topic will include the logic symbol, timing diagram, Boolean equation, and Karnaugh mapping or K-map. The exclusive OR, abbreviated XOR, is similar to OR, but excludes the combination of both A and B being equal to 1. The equivalence is a function that is 0 when the two binary variables are equal. For example, when both are 0 or both are 1. The exclusive OR and equivalent gates are both commutative and associative and can be extended to more than two inputs. The exclusive OR is an odd function. For example, it is equal to 1 if the input variables have an odd number of ones. Exclusive OR is denoted by the symbol plus inside of a circle and is a logical expression that performs the Boolean function shown. It is equal to 1 if only x is equal to 1 or if only y is equal to 1, but not when both are equal to 1. The identities shown apply to the exclusive OR operation. Any of these identities can be proven using a truth table or by replacing the operation by its Boolean expression. This means that the two inputs to an exclusive OR gate can be interchanged without affecting the operation. The exclusive OR and equivalent functions are the complements of each other. This can be easily verified by the truth table for the XOR gate. The truth table clearly indicates that the output y is equal to 1 if only one input or if an odd number of inputs are equal to 1. For example, when the total number of ones in the input variables are odd. For a timing diagram, the binary signal value at the inputs and outputs of any gate has one of two values, except during transition. One signal value represents logic 1 and the other logic 0. Since two signal values are assigned to two logic values, there exist two different assignments of signal levels to logic value. The higher signal level is designated by H and the lower signal level by L. Choosing the high level H to represent logic 1 defines a positive logic system. Choosing low level L to represent logic 0 defines a negative logic system. The two variable map is shown with 4 minterms for two variables. Hence, the map consists of 4 squares, 1 for each minterm. The map is redrawn to show the relationship between the squares and the two variables x and y. The 0 and 1 marked in each row and column designate the values of variables. Variable x appears primed in row 0 and unprimed in row 1. Similarly, y appears primed in column 0 and unprimed in column 1. Moving ahead, a 3-variable map is shown. There are 8 minterms for 3 variables. Hence, the map consists of 8 squares and 3 variables A, B, and C. The 0 and 1 marked in each row and column designate the values of the variables. The M value designates the order in which calculations are derived. The difference in the even and odd functions or where the 1 terms are. For the even function, the The one terms are located with an even number of ones, located in the row and columns. Similarly, for the odd function, the one terms are located where there is an odd number of ones in the rows and columns. This is an example on how to calculate the XOR gate for minterms on an odd function map. The Boolean expression clearly indicates that the three-variable exclusive OR function is equal to 1 if only one variable is equal to 1, if all three variables are equal to 1, or if the odd number of variables are equal to 1. As a consequence, the multiple variable exclusive OR operation is defined as an odd function. The odd function is identified from the minterms whose binary values have an odd number of ones. The complement of an odd function is an even function. The three-input odd function is implemented by means of two-input exclusive OR gates. This concludes Part 2 of the Digital System series. These basics are the foundations to digital logic and Boolean arithmetic and mathematics. I would like to thank Professor Robert J. Michael from Cleveland State University and M. Morris Mono with help on this topic. Thank you.